Hey guys, so good to be back again with you. For those of us that we haven't met before, my name's Bruce, the Part-Time Prospector, and I want to show you a photo that I took a couple of years ago, north of Kalgoorlie, Coolgardie actually, in Western Australia. The photo shows vegetation and rock types on the ground, but the vegetation is showing us what's in the ground. And once you see this photo, and once I point out the aspects of it, you may never look at vegetation quite the same again. In other words, basically, you may never unsee this ever again. So let's jump across to the photo and have a look. Here we got this photo. It's a nice sunny day out in the winter's day out in the Goldfields. And as I said, north of Coolgardie. And we can see there's some rocky ground in the beginning, trees, bushes around, saltbush, etc. It looks like pretty typical southern Goldfields country in Western Australia. But let's point out some things here. And I've got a drawing tool here. And let me just get my mouse to turn up on the screen. So let's swap over to this one. And we're going to do it in white. So what we can see here, and hopefully you guys can see the mouse moving, we've got some barren ground in the foreground. We've basically got a line, if we drew a line along here. And then there's another line along here, separating the other side of the spinifex. So this spiky stuff here is spinifex, and this silvery grey bush in the background is everyone's favourite, the old saltbush. We've got some gum trees, some of them are salmon gums, some are just not. Some more open plain and saltbush out there. And then we've got some trees in the background. So what is this telling me? Well, straight away, there is, as you can say, barren ground in the beginning. And then suddenly it changes into this quite dense spinifex country. Now, not massive, it's only probably 4 or 5 meters wide. But what this is showing is that there's a change in soil type happening here. Spinifex likes to grow in really iron-rich soils. Okay? It's struggling to grow out here, but growing remarkably well out here. So what that is saying is that there's a soil change from there to here. Now, soil change usually, and vast majority of cases, is a change of geology. So the geology here is different from the geology here. And then out here, the saltbush moves in. And then if we change colours, you can see there's a row. Oops, let's get this thing working properly. There's a row of trees that come along here. I'm trying to draw either side of the trees. And then it goes down to the trees in the background. There's only probably a couple of trees wide. It's not very big. But why? Why is there a row of trees and then there's plain, like an empty plain on the other side? Well, and there's no big trees growing out here. Well, things out here there's almost no groundwater out here. Big trees like this need a lot of water. And so you can count on it out here, this line of trees, is where the soil is much, much deeper. And the reason the soil is much, much deeper is almost certainly there's a fault zone running through there. A fault zone, shear zone, some sort of place where the rock has been crumbled and decomposing faster than the surrounding countryside to form what farmers would call an aquifer. Basically a zone where the groundwater is collecting in it. So it's an underground river basically happening there. It may not be flowing, but it's storing water there. At the other side, out here, the soil is deeper than out here, but not deep enough to maintain trees. And then the other side there's another row of trees, which probably means that the soil is much deeper again. Okay, so we've got 3 bits of countryside here. Let's swap colors again. So we've got the stony ground, let's call it A. We've got the spinifex country out here, let's call that B. Then it goes back into the sort of stony countryside out here. So this is back to A. Oops. Then we've got the trees, let's call this C. And then we've got the spinifex country out there. So let's call that D. And we're back into the trees out there on the other side, and that could be a C again. So hopefully you can see that this is actually telling you something that's happening here. I've got another photo of me standing round about this position here and looking in that direction. And you can see how this changes out down to the bottom here. In this photo, where I was standing, you can see the change in countryside here. So let's go back to the pen, go back to the white, and you can see the change happening along here. You can see the spinifex sitting in here. You can see the predominantly saltbush country out here. The deeper red country out here, which is some sort of transported material. And again, if we swap to the blue, you can see these trees run in quite a narrow band. Okay, and then you've got saltbush on the other side and trees out there. So this is actually showing that there's an iron-rich rock in here, almost certainly an ultra-mafic, surrounded by regular greenstone, which is probably, in this case, I think it was basalts and some cherty material, a little bit of biff. Out there was transported cover. And so just looking at the vegetation, you can come up with a subsurface geology map. The vegetation is telling you what's happening here. So let's say, why is there water inside the zone here? So let's have a look at another image. It's just a drawing. I want to show you, let's imagine we do a cross-section through the ground. So we've got the surface of the ground here. We've got some trees growing on top. Oops, we should have some green leaves, not a dead tree. Okay, let's just, for the fun of it, put another tree out here. There is a structure coming through here. So let's put it as a blue line. Now, none of this is to scale. This is just giving the concepts. Now, it can either be a single fault zone, like a single planar crack in the ground, but most majority of these things are not like that. They're generally a shear zone, and it's a zone of intense faulting, breaking, foliation. The rock is basically just messed up inside there. Lots of striations and cracks and whatever coming all the way. And this can go down a very, very long way. What happens, we go back to see if we can change the color here. Let's go to a different color blue. So what happens here is it starts to rain. Okay. And what happens is the groundwater, the rain pools and starts soaking into the ground. It intersects this structured ground and starts to flow down the cracks and the gaps inside the shear zone. Because there's openings and weaknesses in the rock, and some of this will start to break down and form into clay, this starts to weather out faster than the surrounding rock. So if we were to draw in the base of solids, so this is, if we draw along here, so this is the soil out here, and I'm using the soil loosely. It is the non-solid rock, and down here we've got the solid rock. What happens when you get to here is, because this is actually weathering faster than surrounding rock, you end up with a zone that goes like this. And so this is much deeper soil in here. So what you can end up is with a tree that will grow here. The roots have got a long way to go down to get to water. And the water can form down here. Water can be captured in this zone. So if we go back to that original, and you remember that image I had beforehand of the line of trees, you can see why these trees are lining up here. So if we do another diagram and set the canvas, so what we can end up is, if you imagine if we're looking at an aerial view of the surrounding countryside, we've got some small trees, and then every now and then we get some bigger trees. So what is happening here is this, these bigger trees, oops, wrong color. Let's get rid of that one. This is almost certainly the zone of the deeper weathered channel. And it's almost certainly caused by that fault that we did. So that zone where we drew the cross-section could have been a cross-section across something like this. And so you can see how you're looking at Google Maps, looking at the satellite imagery. If you see a line of more denser, bigger, more healthier looking trees versus smaller, scrubbier bushes on the side, is a water channel. And if there's a water channel, there's almost certainly it's because there's a weakness in the rock. Now, does that mean that there's gold in the system? Not always. And it's probably 7 out of 10 times it doesn't mean anything. But it shows you the direction of the channels. And it's worth walking around and having a look. Because a big fault like this, and if we go back to our drawing we had before, and unfortunately I didn't save it, if we go back to here and we had our surface, and I'll do a bit more stylized trees, and we've got our, let's go back to the shear zone. Now inside the shear zone, what we could do is we could potentially have quartz veins coming in. I'll draw it in this color here. And so you could have, and this could be gold bearing. Okay, so here is our solids. Okay, now this is doesn't actually stop at this point. And we've got weaknesses inside here. Now, it's not uncommon for these larger structures to have subparallel little shear zones sitting out here. And inside some of them, they can have quartz veins. And so some of these things can be very rich. So well worthwhile looking. Once you find one of these zones on the map, have a look either side. You might find some quartz on the surface. So the quartz would be building up here, maybe some there, maybe some along there. Just showing where the reefs are outcropping. I want to show you one other thing, which is not talked about too often, is that, I'm going to change color again. And let's go for this purple. Now, as the rain comes down and starts soaking down these channels, it starts leaching elements out of the soil. So many of you, if you've seen the classic regolith profile, you've got the iron cap at the top, and then you can go through this very white clay layer, then you go into the khaki green color at the bottom, and then you go into the country rock at the bottom. So if we go back to the white, this could be the potentially with its organic matter in it. This could be what's I've always called the palette zone. It's basically a white, and then I'm talking very simplistic terms here. You know, this is not a geology lecture in any stretch of the imagination. And down the bottom here, you can have what's called the saprolite, which is the khaki green zone. The rain comes down and starts leaching the minerals out of it. That's why this is a palette zone. Everything's been leached out of it, including minerals that are inside these structures here. Many of these stringers inside here may have contained sulfides, predominantly iron sulfide or pyrites. The pyrite starts to react with the groundwater, and it breaks down to form iron and sulfuric acid. This water being super saline. Some of this groundwater in the Goldfields can be many, many times more saline than the ocean. And so that high level of chlorides can start mobilizing the gold. And so what happens is the gold starts moving out of here and down into a zone where the chemistry starts to change. And so the gold starts to get reprecipitated in this zone out here. And so what you end up with is a zone of enrichment that fits around here. And this can be exceptionally rich. These can be ounces, if not multi-ounces to the ton. With a quartz vein up here, be lucky if you could pan out a couple of pieces, because they're being leached out. Doesn't happen in every single case, but it happens more often than not. Now, there was a case of a gold mine around Coolgardie. When they first found it, I guess the prospectors at the time were more intelligent than we give them, and they actually sold the mine to a bunch of London investors and walked away with a nice chunk of money. The London investors got super excited, thinking that this gold was going to go at depth and a long strike, but all they had intersected was this enriched zone. And the proper name for this enriched zone is called Supergene. And so what they had encountered, this Supergene enriched zone, they pulled it out, made a lot of grade, but once it got to depth, the supergene enrichment ran out, and it was back to just normal quartz veins. If you've got a couple of these stringers as well, they can add to the supergene enrichment, and so you can actually get a very rich deposit. Now, one of the lines of thinking going is that now, it hasn't been proven by science, but that doesn't mean that it's wrong. Okay? Just because something hasn't been proven by science doesn't mean it's wrong. One of the lines of thinking is that as this gold gets leached out of the veins and super concentrated in here and starts intersecting iron-rich saprolite in here, large-scale nuggets are formed. And the gold can be quite high purity because the impurities were left behind and just the gold was mobilized. Now, when I say this hasn't been proven by science, is that the research that's been done at universities and by CSIRO and etc., when they analyze gold nuggets to find their origin, they're only working on a very small number of nuggets. Because how many people want to hand over their nuggets to a scientific organization, and let's say it's a nice, 10 gram, a half ounce, or more, to be chopped up into little pieces, destroyed and looked at, and you'll never get your nugget value back again. And so they're working on a very small sample set. And those they've been given access to at the moment say that nuggets are formed by magmatic processes. But it could just be that they haven't had enough nuggets to play with. And there could be these situations where these nuggets have been forming in these supergene enriched zones. So when the surface weathers down, and let's go back to this thing. Oops, come on, change color. And when the surface can weather down to around about here, okay, this stuff can be exposed to the surface. And rivers can cut through it, concentrate the gold, or you can actually find them with metal detectors. So this is a possible way that another set of gold can form. So going back to my first photos, the vegetation is showing you how to read the geology of the grounds. The next time you're honking along the highway heading out into the bush, keep an eye on the bush, because all of a sudden you'll find that you're going places and it's just like trees on the side of the road. And within a space of a kilometer or maybe even a few hundred meters, suddenly the vegetation changes and you're now open grasslands. Now, unless you're in farming country, and let's assume you're not, you have to ask the question, what happened to the trees? Why did the trees stop growing? And it's almost certainly that you've crossed a geological boundary. You may find you go up a few more kilometers up the road and you're back into the trees again. So the geology is changing as you move along. I hope this information has been helpful to you. If it has, I'd really appreciate it if you give me a like, a thumbs up, and if you haven't subscribed, and you'd like to see more information like this, please hit that subscribe button.